In this second video, we're going to go over more improper integrals. We're going to continue now with integrals that are discontinuous. So suppose that you have a function initially that is positive and continuous. So it looks like the picture that I have over here. The function is going to be well defined on the interval a to v, but on the edge on b is going to have a problem of continuity. It's going to have an issue there. The function f is not going to be defined in b. Okay? So similar as what we did before, we can kind of approximate the area under the curve by considering the area integral with a t close to b by the right side. And so what we're doing is we're calculating this area up to the point t, and then we're going to take the limit when t goes to b by the right side, so we can approximate the whole area in the improper integral. Similar to the infinite area, we look at this as a sound idea, and then we can generalize this overall for any of the two edges. So let's assume that we have the interval AB, and then from a to b we can take the limit to b by the left side of the integral to a to t of f of x dx, and provided that this limit is a finite number, then we can call this integral convergent. We can have the same thing happening with the left side. So disregard here this part. With the interval will be open in a and close in b. Here in this interval here AB, I have a typo. Is again is open in a and close in b. And so for the problem here now is going to be in a. So if the problem is in a, we're going to consider the limit when t goes to a by the right side. So we're approaching by the right side to a of the integral from t to b of f of x dx. And then again, provided that this limit exists and is a finite number, then we're going to call this integral convergent, similar as the infinite case. If the limit does not exist, then we're going to call them divergent. Okay, so we also have a third case where we can consider that this discontinuity is not in the streams, but is going to be in the middle of a and b. And so what we do is we consider what happened if we just take the integral from a to c of f of x and from c to v. If both of those integrals converge, then we can actually define the integral from a to v as the limit of when t goes to c from the right of a to t of f of x dx, and the limit from x going to c by the right side of the integral of s to b of f of x dx. So now let's see some examples of this in action, and then maybe it will make more sense. So first we're going to have the integral from 0 to 1 of 1 over x dx. You might be wondering, where is the issue here? Well, the issue is that f of x equals 1 over x is not defined at 0. So this 0 here is an issue. So what we do is we take the limit when s goes to 0, and remember we're approaching 0 by the right side because we're in the interval 0 to 1. So if we're approaching 0, we can only approach 0 by the right side, and we have the integral from x to 1. Okay, from x to 1 of 1 over x dx. And so this is equals to the limit when x goes to 0 by the right side. And of course, the integral of 1 over x is log of absolute value of x. And this is between s and 1. And of course, this is limit when x goes to 0 by the right side of now log of absolute value of x minus log of absolute value of 1. Now, log of absolute value of 1 is 0, so this goes away. And we're going to be only left with limit when x goes to 0 by the right side of log of absolute value of x. But notice that this log, when it's approaching 0 by the right side, this actually goes to minus infinity. The log, if you remember the graph of the log, when we're approaching 0 with the log, is going like in this direction. Well, I flip a little bit. The log is doing this. So the closest that it gets to 0, the more closer is to large values. And so this is going to be minus infinity. So overall, what that implies is that the integral of 1 over x from 0 to 1, the x, is minus infinity or diverges. Now let's go with a second example. Now let's consider this integral going from 0 to 3 of 1 over square root of 3 minus x dx. So the problem here is clearly x equals 3. Because for x equals 3, we have a case that do not exist for the function f, right? So what we do is we take the limit when x goes to 3 by the left side of 0 to s of 1 over square root of 3 minus x dx. So if we rearrange this to integrate, we're going to have that this is just 3 minus x to the minus 1/2. And so when we integrate, this is essentially minus 3 minus x to the 1/2 over 1/2. So this is essentially going to give me a 2 here in front. So it's minus 2 here. And now this is going to be the limit when x goes to 3 by the left side of minus 2, 3 minus x to the 1/2 of between x and 0. And so plug in the limits of integration. We have that this is minus 2, 3 minus s to the 1/2 minus, and now I plug 0 here. So plus 2 times 3 to the 1/2. Now when x is going to 3, then the factor 3 minus x is going to 0, and the square root of 0 is 0 as well. So this is going to be 0 plus 2 square root of 3. So this means at the end that the integral from 0 to 3 of 1 over 3 minus x dx is going to give me 2 square root of 3, and this is a convergent integral. Alright, so now let's move on to another example. Now, improper integrals also work with most of the common integration techniques that we have, and we just got to be careful that we're just replacing the problematic endpoints at the very end. So for example here, we do have problems in both of the extremes. We have issues in -1 and 1, because in both of these cases the denominator is not going to exist. So we have issues in x equals -1 and 1. So in this particular scenario, what we want to do is break it apart. We're going to break it apart to a point in the middle where we don't have any issues, which is 0. And we're going to have two integrations. One from -1 to 0 and one from 0 to 1. And we're going to expect that both of those give me numbers. And if they do, then in that case, the integral is convergent. Otherwise, it's going to be divergent. So we're going to see this is the limit when t goes to -1 of t to 0, x 1 minus x squared dx, and plus the limit when x goes to 1 of the integral of 0 to x, x over 1 minus x squared dx. So now let's forget about the limits of integration, And let's think about the integral. We're going to use a substitution u equals 1 minus x squared, and then the du is going to be minus 2x dx. Notice that we have the x in there, so we kind of going to put the minus 2 below, and then we're going to get the x dx. And so on both scenarios, what that's going to produce is that we're going to have an integral of the shape 1 over square root of u du minus 1/2. And so notice that this is essentially u to the minus 1/2. So this integrating this is going to be twice u to the 1/2 times minus 1/2. So at the very end, when I integrate both of these things, I'm going to get minus u to the 1/2. And that's going to be for both of these integrals. So now I can come back to the limits of integration. So this is limit when t goes to minus 1. And this is going to be minus 1 minus x squared to the 1/2 between t and 0, plus limit when x goes to 1, the same thing. And here's between 0 and x. Notice that when I plug in 0, I'm going to get just 1 here, and the square root of 1 is 1. So I get minus 1, and then plus limit when t goes to minus 1. And by the way, here I'm doing minus 1 by the right side. It doesn't matter too much in here. And here limit x goes to 1 by the left side of minus 1 minus x squared 1/2. It's important that we have different limits, different variables, because these two limits are not approaching the same number. Okay, so we cannot have the same variable. When I plug in here minus and minus is going to be plus, so plus 1. And so now you can see that this minus 1 and this 1 are going to go away. So cancel out with this. And now it's going to be the limit here. When t goes to minus 1 here, this becomes the square root of 0. So this is going to be just 0. And similarly here, when this goes to 1, this becomes 0. So both of these cases is 0. And the integrals here is just going to be 0. So we can consider that overall the integral of minus 1 to 1 of x over 1 minus x squared dx is 0 and is convergent. Now let's do one more example. And here we have the integral from from pi to 2 pi of cosine of x over the square root of 1 plus sine of x. And this is a very similar situation to what we had before. We have a square root, and we clearly have a root that is going to be in bold after we do the substitution. But where's the issue? The issue is if I find a point where the square root below is going to become 0, which is going to happen when x is equals in 3 pi half, since sine of 3 pi half is minus 1, and so that means that the below will be 0. So this is an issue, and notice that this is in the middle. So now I gotta do two integrals as well. I gotta do the integral from pi to 3 pi half of this, and then plus from 3 pi half to 2 pi, the same thing. So it's kind of similar to the exercise that we did before, but in this scenario we have actually the issue being in the middle. And before we had the issues in the extremes, and so we were going for limits in the extreme, and here I actually gotta find out where the issue is and split my integral in there. How to solve the integral is very standard. The problem becomes in 3/2, so we call this limit when t goes to 3/2, 3 pi half, and in here is going by the left side, and we have the integral from pi to t. And in here we have a similar situation, but here we're going by the right side, and it's limit when x goes to 3 pi half by the right side. And again, just to be safe, because I don't know if we're approaching using the same numbers, then we use a different variable here. Now the integration is as what you will expect, 1 plus sine of x, and so the du is cosine of x dx, and so you can see that their integral are right there, and this is just gonna becomes again 1 over square root of u du, and we already saw how this works out. This is just going to be u to the minus 1/2, so this becomes u to the 1/2 over 1/2, so 2 u to the 1/2 in here. And so now this is limit when t goes to 3 pi half by the left side of 2 the square root of 1 plus sine of x, in between pi and t. In here, similar situation. Now, when you plug in 2 pi, sine is 0, so that this becomes 1. So in this situation, we're going to have the limit when t goes to 3 pi half of 2, 1 plus sine of t to the 1/2 minus, and this becomes a 2. And in pi, sine of pi of 0, so this becomes 1, so this whole thing becomes a 2. And on this case, a similar situation happens. Here I'm going to have minus here, and I'm going to have plus and the 2 pi. And so now we have the minus 2 and the 2 that cancel each other. And then again, when this 3 pi half is plugged into sine of t, it becomes minus 1. So this becomes a 0. So again, we have a case of 0 plus 0. And then again, we have that this integral is 0 as well, and it's going to be convergent. So these are some cases that illustrate how to go ahead and deal with discontinuities in the interval. Okay, in the last video we're going to actually go ahead and see certain integrals that we cannot directly calculate, and so instead what we do is we compare them with some other complicated integrations or with some other improper integrals that we can use to just check their behavior and classify them as convergent or divergent.